In this tutorial, we're going to be looking at variables. So what are variables? Well, sometimes in our program, we're going to be working with numbers that are rapidly changing. So these are going to be possibly from sensors. Maybe we're counting how often something happens. So they're going to be changing numbers. And quite often we're going to need to save these numbers somewhere, and we're probably going to be saving them into our SRAM or into our RAM. Now SRAM is readily available. We can pull numbers in and out of it without affecting our overall program. So think of our program that we write is a fixed state. We don't want to change it too much as we're looping around in our constant program cycle. But the variables are numbers that will be changing. These could be values from sensors or counters or anything like that, maybe timing functions or counting seconds that have gone by. One thing to note is there's three main types of memory available on our UC or our microcontroller, and these are typically going to be the flash memory. Now, different microcontrollers have different amounts of memory. But for our 328P, which is on our Uno board, we have 32 kilobytes of flash memory available. This is where we'll actually store the program. Our program is stored. And the only time that we actually write to the flash memory is when we press this upload button here. So we press the upload button. This program that we've written gets stored into our microcontroller and it's saved into the flash memory. Once we've actually done that, there we go. Once we've actually done that, we're not going to be changing things very often in there. We're going to cycle through, execute what's in there. Any numbers that need to change, we're typically going to put them into our variables, and we're going to be putting that into the RAM or the SRAM. So it's actually called static random access memory, but we can call it RAM. Now, how much does this microcontroller have? It actually has 2 kilobytes of SRAM on it. And bear in mind, you want to look at the data sheet. You actually pull up the PDF data sheet. Let me see if I can pull up the data sheet now. Here we have the data sheet. And we can see that this is for this Atmega 328P, which is on the Uno boards, and a lot of the other boards as well, but you do need to double check because they're not always the same chip. And we can see there we have this 32 kilobytes of program memory. We have this 1 kilobyte of EEPROM, and we have this 1 kilobyte of SD RAM. Down here we've got a little bit of information down here, which I'll come to in a minute. So we have our RAM. This is where all variables will be stored. And then finally we have something that's called electrically erasable programmable memory. And that's actually written down as EEPROM, and we get 1 kilobyte of EEPROM. Now in this example, I'm not actually going to cover the use of EEPROM, but I will just cover it briefly what it does. So EEPROM is a permanent memory, and by permanent memory we really mean non-volatile. So if I take the power off my Arduino, unplug it from the USB port, stuff that's saved in the EEPROM will remain there. But typically we won't be using it very often. You know, we want to be changing these numbers rapidly, and unfortunately EEPROM has got a limited life cycle. So it's limited life cycle, and that limited life cycle is around about 100,000 read-write cycles. So we call it cycles. And that means that if we actually write to it more than 100,000 times, it may stop working. I think it's important to mention that the flash memory has about a 10,000 cycle lifespan. And really, if you think every time you're going to press the program button and upload to your Arduino, you're going to be hard pushed to exceed 10,000 cycles. But let's think if we were looping around in our code, and we could be looping around, you know, millions of times a second or thousands of times a second, we could very quickly run out of EEPROM. So typically EEPROM will be used to save things occasionally that we want when we boot up. So that might be things like user settings. Let's say screen contrast, that might be one. Let's say we've made a bike computer that tells us how many miles we've travelled. If we take the power off that, we might actually want it to save how many miles we've travelled, and when we plug it back in or power it back up, that value could be loaded from the EEPROM, put back into the SRAM, and then we've got that value that we were last using. But we do need to create some sort of program that will actually make use of the EEPROM, and that's really a tutorial in itself. So I'm going to kind of skip past EEPROM now, but just make you aware that there are those 3 different spaces of storage. So as mentioned, the flash is where we'll be storing our program, and all variables and all values that will be rapidly changing will go into our SRAM. So before we can put a variable into our SRAM, we have to make kind of a container. I believe it's called a container. Just imagine you need to save some shoes, you need to put them away. You need to choose an appropriate size container. Let's say we've got a very small resistor. We probably wouldn't want to store the resistor in a shoe box, it would get lost. We would place our shoes in the shoe box, but we would use a much smaller container for the resistor. And essentially, because our RAM is limited in size, we're going to create containers that are most appropriate for the values we're going to save. For example, if I need to save 3.5 million as a number, I need a much larger container than if I was just going to store 1 or 20 or a very small value. If my maximum value is only ever going to be 20, I'd be using a very large RAM location or a RAM space to store a small number. Hopefully that makes sense, but essentially we need to be very conservative on how we are using our RAM. So what we're going to be looking at is what kind of packages can we make to save variable data in, or varying numbers. I'm just going to put some notes in here and say we need to choose the right container for the value range we're working with. So I'm just going to give you a quick example here of a variable, and it's one that we might use quite frequently, and I'm just going to do what we've done a few times before and just go kind of int or int. That actually stands for an integer, and then we're going to call this space, we're creating this integer package, which is 16 bits, and 8 bits is a byte, so we could say it's 2 bytes in storage, and we've got 2000 bytes available. So let's create this variable, and we'll call this one counter. We're going to count how many times something's happened, and when we start the program up, we would always want the count probably to be 0 unless we've saved it in EEPROM, and then it would load it from EEPROM and it would make that count whatever was saved there. But for now we're just going to say we'll make it 0 every time we turn on. And what we've done here is we've created a variable which is an integer in size, and what did I say, that was 16 bits, and we've saved the value, or put the value 0 in there. We've also given it a logical name, and that name was counter, so we'll probably be using it for a counter. We don't always need to put 0 in there. Let's go for another example. We could say int, and let's say we've got an LCD display and we want to adjust the contrast. If it's very low contrast, we can barely see it. If it's very high contrast, it might turn the whole screen black. So we'll type in a new variable here and call it contrast. And because we want something preset, and we'd have to do a bit of testing to figure out what the correct value was, but let's just say I've done some testing. 20 was too low, 70 was too high, and I've ended up honing in on the number, and we're going to make contrast 50. So that's another thing we can do there. And what that's going to do is when we power the Arduino up, when powered up, it's going to set the contrast to 50. And of course, if we power off, it's going to default back to 50, because that's what we've written it in the program. we could make a program that adjusts that value. So we can have some buttons that kind of increment contrast up and down, 51, 52, etc. But what's going to happen is when we power it off, we're going to lose that data unless we use that EEPROM. So let's actually focus in on what does int mean. Well, int is the type of package, and we've said that that package is 16 bits, 16 noughts and ones long, so I could write that out. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's how much of the memory we've used. If I make this value here 1, depending on which one is the most significant bit, let's say that this is the least significant bit, this value would of course be 1. If I made that 1, 0 there, this would actually now represent a value of 2. If I make both of those 1 and 1, we've got this value is 1, this value is 2, so that value would now be 3, and so on. I'm not going to go through the whole cycle all the way up, but that is potentially what we could have with the maximum number being all 1s. So what we'll look at now is a range of examples of these containers we can use to actually save our data in. Do note that these examples are only valid for the 328p. What I mean by that is if we actually use a different microcontroller, these could create different size containers. So could be different sizes. So you'd actually kind of need to look up the table, the data for that chip, and figure out what it will create when you use these commands. Right, so let's start off with the int, or the integer, and I'm going to come across, let's come across some tabs here, 1, 2, 3, 4, and I'm going to do another one there. And what does that mean? Well, int is going to create a container or a package that has a size of 16 bits. There we go, 16 bits. And it will hold a value between, let me think of that, minus 32,768. And it will hold a maximum value up to 32,767. So note that this int value can store negative number and a positive number. It can also store 0 in it as well. But if you try and store a bigger number than 32,767 or a smaller number than minus 32,768, we're going to have what's called an overflow event. We might actually get some data back that isn't correct, or we might flow back around and come out the other side. Make up a little example program where we put 32,767 into an int, and then when we loop around we can add 1 to it and see what number comes out. But essentially we would lose track of the number unless we recorded that event happening somehow, which is possible, but we won't go into that right now. So if we need to hold a bigger number than that, we could actually move over to something called an unsigned. We'll write this one in, unsigned int. Hopefully that kind of makes sense, but it's still a package size of 16-bit, or a container size of 16-bit, and it will hold a value between, just correct that there, it will hold a value between 0 to 65,535. So now you can see we've got a larger top end number, double really, and we cannot go into the negative. Hopefully that's logical because we put unsigned on the front. So by saying we're never going to go into a negative number, we've expanded our positive number storage range. So the next one we'll look at is called a short. A short is again 16-bit, so size of 16 bits. The value we can store in that is actually the same as the value for the integer. So it is going to be minus or negative 32,768 to 32,767, Why have we used a short instead of an int? Well, the int varies depending on what chip you're using, whereas short works across all UCs. So it works across all UCs as 16-bit storage. So sometimes if someone is writing a program that they're not sure whether the user's going to end up pulling it on an Uno or a Mega or a Nano or some other chip, they'll probably use a short instead of an int. So if you find some online program and you're copying it, or you're modifying it rather, to work on your chip, you could use an int. But I think the Arduino Uno will also accept short, so some people prefer to use that. And again, the exact same example, we can have an unsigned. Unsigned short. And again, that is going to be the same as above, 16-bit. It's going to store between 0 to 65,535, and it's going to work across all of the microcontrollers there. So we'll put that one in. So the next one, we're going to step up in size, and this one's going to be called, it's a long. Long is 32 bits in size, and this is going to store a much larger number. So this one can store -2147483648. So let me think how big that number is. Hundreds of thousands. Oh, I've lost count already. Hundreds of thousands. So it's 2,147,483,648 negative. And that's going to go up into the positive scale into 2,147,483,647. So we've got a very big number there stored, but we're using up 32 bits now. And likewise, same as above, we could have an unsigned. So we could actually shift that storage space by saying we're not going to have any negative numbers. It's only ever going to be positive. And to do that, we're going to have a value between 0, and now we're getting to 4,294,967,295. So kind of quite a massive number there. And what comes after the unsigned? Oh, sorry, I've messed that one up there. So it's an unsigned long. So it's the same as the one above, but now it's unsigned. Let's actually move these out a bit so we've got them all in line. So the next one we're going to cover is called a float. A float is very useful. And the float is again 32 bits in size, so it's 32 bits. And the float is the only variable we can use where we can actually save a decimal point or a decimal place. Actually, I think there's another one as well, but we'll say for now we can store our decimal place in here. And we can have a value between -3.4028235 10 to the positive 38, or be actually -38, but we can go e to the 38. And that will go all the way up to a 3.4028235 e to the 38 again. So there, e38. So in total we can have up to 38. But one thing to note is we can actually move this decimal place. So we don't have to store just one whole number and all these all these fractional numbers down here. We can actually move this point. So we could actually use, we could be, 32,000.925 or something like that. Or we could store something like 1.56141. I'm just putting random numbers in there. But we can actually let that decimal point move. Note it is signed, so we can go into the negatives, but there is some limitations to this. And off the top of my head, I think really we can only go down to about 5, maybe 7, 6 or 7 points after the decimal point. I'm just going to do some experimentation, but I'm going to leave it out of this video. But what you'll find is when you start putting more than 7 numbers after the decimal point, we start getting accuracy errors and things just don't work properly. There's also a limitation to how many digits you can have on the top side, and the more digits you have on the whole side, we'll call that the whole side, the less digits you can have on the fractional side. So bear that in mind, but for many beginners, they want to save a small number with a fraction on the end of it, and they're trying to put it in an int, and it just won't work. It's got to go into a float. Next one we have is called a char, a character. A char is a smaller package, so it's 8 bits, and it will store a negative number of 127 to a positive number of 128, but it can also store things called ASCII characters. And if you're not sure what ASCII characters are, that is kind of the letters of the alphabet. So letters that come off the keyboard, it can actually store them in there, and when you pull them out, the kind of environment knows that you're pulling out an ASCII character, and it can handle it as a letter. Believe one char can only hold 1 letter. And then we also have our unsigned char. There we go, unsigned char. That is also 8-bit in size, and that will store 0 to 255, and it's also able to store these ASCII characters. No problem at all. Okay, so now we come down to one called a double. Let's do the double. Double is fine, there we go. The double is actually a larger size. It's going to be 64 bits of noughts and ones, so we're now eating into 64 of them, but it can store, again, very large numbers. 1.7 and e to the minus 308, so very large negative number, to 1.7 e to the positive 308. So yeah, massive. And I do believe there is one bigger one than that. Let me see whether I can find that. So the one I'm thinking of is called a long double. There we go, long double. And that one uses up a whopping 80 bits of memory or RAM. And that one will allow us to store values down to negative 3.4 times e to the 4,932, all the way up to 3.4 times e to the 4,932. So really massive numbers there, really big numbers. I can't remember off the top of my head what that would equate to, but you could pop that into your calculator. 3.4 exponential 4,932 would give you the maximum value we could store in there, and it's going to be really big. And then there's one more interesting one I'll just cover. That one's called Boolean, B-O-O-L-E-A-N. And Boolean can only have 2 states. It uses up 8 bits of data, and it will either store true or false. So it can only store one or the other, no other statements. You could put 0 or 1 in there. That would also work. They're basically 0 being false and 1 being true. And the advantage of this one is that we can only store those 2 options in it. We can use it for checking if something's happened, or has a button been pressed, or has an event happened that we need to keep track of. Well, that's it today. Bear in mind, this code that we've created here won't actually function, but it's just a set of examples that shows you the types of variable packages we can create, how much RAM they use up, and the minimum maximum values that we can store in each. And if you don't keep this, bear in mind you can kind of get hold of charts and stuff off the internet. If you type in variable types Arduino into Google Image Search, you're going to find various tables that will show you all of these and explain these details. Well, okay, thanks for watching, and catch you next time.